All right, folks. Well, welcome back. Hopefully, everyone's doing okay. Um, just real quick, I want to remind you folks that if you have any questions, please make sure you email me and let me know what's going on, what your questions are, and if you have the time, if you can come by, I will be here after school today, 1:30 to 2:30. I again Tuesday and Wednesday this week kind of threw things off with the meetings that I had after school. But I didn't see anyone yesterday, so please make sure you stop by today after school with our Zoom meeting if you have any questions, 1:30 to 2:30. Okay. All right. So with that said, let's go ahead and let's start today with this particular problem here. More practice with the stoichiometry. Stoichiometry is a very important part of chemistry, so it's something that you'll need to make sure you know, especially for those of you who are planning on going on and you have to take more chemistry. This is something that's going to be a skill that you have to learn and you have to be able to do if you want to be successful as you move on in chemistry. Okay, so not only for our class, but also as you move forward, like I said, for those of you who plan to continue on in science, whether it's in medical school or it's with any of the sciences, you'll need to be able to do this. Okay, so let's go ahead and let's take about a little less than 5 minutes. I don't think it should take you that long to do these problems here. So read this problem here. It's number 8 in your problem set. Take a few minutes to work on this, and then when we get back, I will work this problem out for you. Okay, so go ahead, get started with this problem. Okay, so let's go ahead and let's work this one out. This is a stoichiometry, so make sure you understand then that with any of these problems, you always have to make sure that you have a balanced equation first. Don't assume then that what you're given is balanced, and this problem is not balanced, so it's not balanced. So let's go ahead and let's make sure we balance this problem here. So if you balance this problem there, and if you have any questions on this, please make sure you come see me. It's uh, 3 and 2 here. Okay, so 4, 3, 2 will balance out this particular problem. Okay. All right, so with that said, then I would also recommend that you write down what they give you. This time they give you then the mass of the product that forms, so 583 grams aluminum oxide that forms. Okay, from here then it's going to be 2 conversions that you have to do. So let's make sure then that you're able to work out these conversions here. And I'm just going to work these out for you. Okay, and make sure if you have any questions, you come by and you see me. So let's go ahead and let's do the first one. So we start out with this time. The question then is, how much of the aluminum will form? So what you're given then, what you start out with then is 583 grams of aluminum oxide. Okay, so that's what you start out with in this particular conversion. Obviously, this is a product, so you're not starting out with this in the reaction itself. It is what you end up with. But for the stoichiometry, for the math, then for the conversion you're going to do here, then what you are asked then is you're asked if you produce this much of aluminum oxide, how much of each one of the reactants do you start out with? So therefore, it seems a little bit odd to say then that you're starting out with this amount here, but this is the conversion. So the conversion, remember, you have 3 questions you have to make sure you answer. What do they give you to start out with? What do they want you to solve for? And what are the conversion factors that you need in order to get that conversion done? So in this particular problem, they give you the amount of the product to start out with, and that's your aluminum oxide. What they're asking you to solve for then is the amount of the aluminum that is equivalent to it, which is how much you need to start out with. The conversion factors then will be the molar mass of aluminum oxide, the mole ratio of aluminum oxide to aluminum, and then finally the molar mass of aluminum. So we're going to start out, we're going to divide by the molar mass of aluminum oxide, since we're starting out with the mass of aluminum oxide. So since we have a mass here of aluminum oxide, we're going to divide by its molar mass, which is going to be 102 grams per mole. So make sure you can get that. Okay. Mole ratio here is going to be 4/2, 4 moles of aluminum over 2 moles of aluminum oxide. Okay, and then finally, then we're going to multiply by the molar mass of aluminum, which is going to be 27 grams of aluminum, 1 mole of aluminum. So make sure you are able to figure out where we get these molar masses from, why we divide, then multiply over here, and where we get the mole ratio from. Okay. All right, so if you get that, you get your answer then. It's 309 grams of aluminum. Okay, so that's how much aluminum you need to start out with to get 583 grams of aluminum oxide. Okay, so the second conversion then is going to be very similar to the first one. Okay. This time, what we're going to solve for is not aluminum. We're going to solve for then the mass of oxygen. Okay. All right, so again, 3 conversion factors that we're going to need in order to get this done. Okay. First conversion factor again is molar mass of aluminum oxide, Al2O3, 102 grams, Al2O3. This time the mole ratio is going to be a 3:2 mole ratio because we need the molar mass of aluminum to, of oxygen to aluminum oxide. So therefore, then it's going to be 3 moles, 3/2, oxygen, 2 moles of aluminum oxide. And then finally, the molar mass of oxygen is going to be 32 grams oxygen for every 1 mole. All right, so plugging that in, you'll get your answer then here as being 274 grams of oxygen. Now, a few of you may notice then that if you remember law of conservation of mass, you really don't have to do this second conversion here. Remember, with conservation of mass, let's say you just solve for aluminum here, whatever that is, it has to be, you can solve it for the mass of oxygen by taking the total mass that you get from this combination reaction, subtracting it from the mass of the aluminum, and you should also get 274 in that case. Okay, so either calculation will work, either way will work. Here, using the law of conservation of mass, that saves you a whole lot of work in terms of having to do the conversion. Okay. All right, very good, folks. So let's go ahead then. If you have any questions about this, remember, make sure you come by and you see me and get your questions answered. Okay, so I'm sorry, let me go ahead and put that on. Okay. All right. Let's go ahead and let's take a look at where we left off with yesterday. Okay? And we were talking about pressure. We were talking about how pressure can be, how we can determine pressure and how it's related to force. Okay, so we saw yesterday then, and let's go ahead and let me quickly review this for you. We saw then that pressure was proportional. Okay, that means that it was dependent on force, the force that's applied by an object. Okay? So the little fish symbol here just means that there's a relationship. It's a proportionality symbol in math. And so with that said, then pressure then can be defined in terms of force. Force can affect the pressure. And so I pointed out to you then that if I step on your foot, and let's just review this real quickly. I move, I push down on your foot, I'm applying a force on your foot, a downward force on your foot. And so you can feel that because you are, you're feeling the pressure of the pressure is coming from the force of my foot or my weight. If I stepped on you, my full weight, the weight of my foot, my weight pushing on your foot, that's where the pressure comes in. Okay. And so we clearly understood that. We can see that happening because if I change and I had an elephant step on your foot with the full weight of its full weight, you would feel a greater pressure here. Okay, so we talked about that, and we said then that in this particular instance here, you would feel a greater force because the force, Mr. N, my weight, is less than the force of the elephant. Okay, and so therefore the pressure that I exert is going to be less than the pressure that the elephant exerts. Okay, so that, with that said, then I think that makes it pretty obvious that the force is absolutely related to the pressure that that an object feels. Okay? All right. So with that said, then I asked you to consider what would happen then if I stepped on your foot with a pair of high heels. Okay, so we talked about this as well. And I left you with this question yesterday that I wanted you to answer. And so we see that in this particular case, okay, that my force doesn't change, my weight doesn't change, because my weight, whether it's stepping on your foot with a pair of shoes or stepping on your foot with a pair of high heels, okay, my force doesn't change. So that cannot explain why the pressure changes. But we do know this, folks. We do know this, that the pressure that you feel here when Mr. N is in shoes is going to be less than the pressure that you will feel when I'm in heels. Okay. And so the question then is, why is the pressure greater when I'm wearing heels than when I'm wearing my shoes here? Is there another factor that determines pressure besides the force here? And the answer hopefully you came up with is that there is. There is a second reason why, and let's explore the reason why here. So if you can imagine then, if you take a look at the area of this here, so the area when I'm wearing a shoe, versus the area of contact. Now let's go ahead and let's just focus in on this here. The area of contact, okay, when I wear the heels, in these two areas, which one is greater? Well, obviously, let's go and take a look at this in the area over which my shoe steps, the area of the shoe is going to be greater than the area of the heels. Okay, so again, if you just take a look at, and you can kind of imagine this, just take a look at the pair of heels here. The overall area of the particular heel here is going to be less than the overall area of the shoe. So the area of the heel is less than the area of the shoe. So I'm applying the same force, but I'm applying the same force over a smaller area. And so pressure then is also going to be affected. Pressure then will also be determined by the area, but not directly here like we have with the force, but it's going to be inversely proportional. And what does this mean then? You can imagine this. As the area over which we apply our force, gets smaller. As the area gets smaller, the pressure is going to increase. So that's what this particular relationship points out to us here. This is telling us then that the pressure is inversely proportional to the area. So as the area gets bigger and bigger, you can imagine this, as the area gets bigger and bigger, the pressure is going to get smaller and smaller. Okay? So there's two factors then. There are two factors that will determine the pressure that an object exerts on another object. Okay? And we can relate that into the equation here for pressure. Okay? So the equation here for pressure then allows us to see then the relationship between force and area, okay? And how it affects pressure. Okay? All right, so with that said then, we see here then that as force increases, the area is going to increase, the pressure is going to increase, and as the area increases, the pressure decreases. So we have established, we have brought together this relationship and this relationship in this equation right here. And this is how then we can solve for pressure if you're asked to solve for it. We can solve for pressure if we know the force and we know the area, okay? And so that's the way that we can determine pressure, okay? And so we're going to use this equation here, and we're going to use it quite a bit. And I'm going to use it in the analysis of gas pressure, because you can imagine this. We already said gases are in constant motion. They're always moving around. And as they move around, if they bounce into something, they're going to push into it. They're going to apply a force on that particular object, whatever it may be. And since if you can imagine this, all gas particles is big, small spheres, if we can think about it that way, then that means that when they make contact, in an area with an object, whatever it may be, that area of contact they will also have an area of contact that will be very, very small. So if they're moving and they push in on an object, if they make contact over a small area, they exert a force. Okay, so they exert a pressure. Okay. All right. So with that said, then let's go ahead and let's continue on with what we have here. Okay. All right. So with that said, then let's just quickly review here. All moving bodies then will exert a pressure. Okay, they will exert a force. Why? Because they're in constant motion. Okay, so everything that's in motion will, once it comes into contact with something else, will exert a force on any other body. Okay, so you can imagine with the gas particles. Okay? As they're moving around, they're going to bump into everything around them. We talked about this, and that's the reason why they have the nature of their motion is random motion, because they're bumping in, they are colliding with everything around them. Okay, so the collisions that occur then, okay, you can imagine this, when they collide, okay, they're going to push on to another gas particle. They're going to push on the walls of the container, whatever they're in. As they're moving around, they will collide more. Okay, so you can imagine this when you have not that many gas particles, when the concentration, when we talk about concentration, we're talking about how much we have. When the concentration is low, we're going to have less collisions. And so with less collisions, then you're going to have less force being exerted by each of the gas that you will experience there. And then if you have a high amount, if you have a lot of gas particles, you can have more collisions. Okay, and so make sure you understand this: more collisions when it comes to gas particles will mean then more force. Okay, so make sure you keep this in mind. So if you have low concentrations, a small amount of gas particles, you have fewer collisions. You have a lot of gas particles, you can have more collisions. You want to keep this in mind because we're going to get back to this discussion. We will get back to that relationship in just a moment here. And so we can write out that relationship in this way here. Okay, so let's go ahead and do this here. And continue on with the discussion of forces here. So a number of collisions. So let's write it up here. Number of collisions, number of particles. So basically low concentration versus high concentration. Number of particles is directly proportional to number of collisions. Okay, so make sure you keep that in mind. So we have that relationship here that we can use. So the number of I'm sorry, let me go ahead and I'll write this a little bit more clearly for you. Sorry, a little bit messy, difficult to see. This is number of particles. Okay, so the number of particles is directly proportional to the number of collisions. As you increase the number of particles, that is, as the concentration increases, you have more collisions. And then so down here, then as the number of collisions, so the collisions then increases, you see then that the force will also increase. So there are two proportions here, two relationships that we have to take advantage of. First here, then the number of particles as it relates to the number of collisions. And then secondly here, the number of collisions. As the collisions increases, the force will also increase. As the collision decreases, the force will also decrease. Okay? And so on a macroscopic scale, we can see then how gas particles, as the number of gas particles increase, the number of collisions will increase, the force that particular gas exerts will also increase. Okay? And so going back to our example of our balloon, if at the very start of this discussion we talked about, as we put in more and more as we blow into the balloon, as we add more gas particles into the balloon, we are going from low concentration to high concentration. So as we add more gases, as we inflate the balloon, what we're doing then is we are adding more gases. As we add more gases, the gas particles inside that balloon will bounce, will collide with everything around it, especially the walls of the balloon. And as they do so, they collide more often with the walls of the balloon. The force the gas particles exert will increase as well. Okay? And so, yeah, obviously, if you take a small amount of gas, if you an individual gas particle really doesn't exert that much force because it's so small. It's very, very small. You have one single gas particle. Okay? But the cumulative effect of having many gas particles, and as you add in more and more gas particles, those gas particles will obviously increase the pressure that they exert. Okay, so make sure you keep that in mind as we move forward. Okay, all right, very good. Let's go ahead then and let's take a look at just to quickly summarize this up. So we can say this then with at the conclusion of our discussion, we can say this then that as the pressure that the gas exert, the gas pressure is going to be a result of the collisions of the gas particles. Okay? And so that's what you want to make sure you keep in mind. And as you move forward, the number of collisions can be determined by how many gas particles we have, the amount of gas particles we just talked about in the previous slide. Okay? And one other factor that we're going to talk about, and that is how fast those gas particles move. Okay, and so keep that in mind as we move forward. Okay, and let's go ahead and I want to ask you this question here. Okay, so I'm sorry, that's quick, and then I want to ask you a quick question just to wrap things up. Okay, so we can sum up then that pressure and force and area, that we can determine the pressure by determining the force. over which an object moves, the force the object applies when it is interacting with some other object, and the area over which they interact. Okay, and so we said then gas particles will, as they move around, they will exert a pressure because they will interact, they will collide with everything around them, and the number of gas particles. That's what this mass is supposed to represent. So if you have a high amount, if you have a large concentration of gases, the mass will be greater. You have more particles floating around. Okay, so we talked about. So the question I want to ask you then is this: okay, at what point then? So we know then that gases exert pressure because they move. Okay, we know then that as they move around, they collide. They interact, okay, and so they will exert a pressure. Okay, my question to you then is, at what point then do gases exert no pressure? Is there are there conditions in which the gases exert no pressure? That is, the pressure here is at 0 atmospheres. I mean, the pressure, when you measure the pressures, is there a set of conditions, set of circumstances where the gases no longer exert pressure? Okay, and the answer is yes. The answer is yes. So you can imagine this: if there is no gas, or if there are no gas, if they have no mass, okay, is there a situation, is there a condition in which the gases no longer have mass? Okay, so let's consider that. Okay, so yes, so when there's no mass, the gases no longer have mass, they can't exert pressure, and when they are not moving. Okay, and so what I would like to do then, and I'm running low on time here, on Monday, I want to do an analysis. I want to talk about then, we're going to do the analysis using some math, a little bit of math, and the equations that we use. But I do want you to consider this and make sure you look in your book and kind of prep yourself for this. Okay, that is, we can determine this. We can use the two simple formulas that I gave you. We can use a couple of simple formulas, and I want you to try to consider this here. Okay, that is, if we know that pressure is force over area. Okay? If we know then that force, using Newton's second law, is mass times acceleration, and then finally then we know then that acceleration is the change in velocity, change in motion over time. Okay? I will be using these three equations here, okay, to answer this question. To answer this very simple question, we will use those three equations to see how it works. So, make sure you understand what each one of those equations tell us. Okay? And in physics, folks, equations are always used to identify or to describe certain phenomena, okay, that we can observe. And so make sure you are able to use these three equations to understand what they mean. And then I'm going to use these three equations to answer this question: when do gas particles no longer exert any pressure? Okay. All right, so we'll talk about that on Monday. Okay, so you folks have a good weekend, and what we'll do is we'll pick up with this discussion on Monday. Okay, have a good day and have a good weekend. Again, hopefully, if you have any questions, email me, or make sure you stop by after school today, 1:30, 2:30, get your questions answered. Okay. All right, folks, I will see you on either after school today or on Monday.